Hello and welcome back to Historical Geology, and today I'm going to talk about Chapter 5 on rocks, fossils, and time. Now, one of the things your book mentions in the introduction is how sedimentary rocks in particular capture Earth's history in terms of sedimentary processes, fossils, and preserve this in this geologic units. And also we're using this principle of uniformitarianism to help us interpret those same processes that we see happening today. We can use them to help us interpret the geologic past. Now, stratigraphy is just really a branch of geology that's concerned with the sequence of events, the order of the rock units. And the rock units can be igneous rocks, metamorphic rocks, sedimentary rocks in particular, because they're the ones that are stratified, that occur in these layers. But we're really looking at all types of rocks, and we can put them in a geologic order from oldest to youngest. So stratigraphy, again, deals with mostly sedimentary rocks, but again, we can be using igneous and metamorphic rocks. And then we also try to look at not just the vertical relationships, like in a canyon wall, but also lateral relationships. In fact, here's Walther. He proposed that in any stratified sequence, when you're looking at a vertical sequence, in this case we have beach sand, and on top of that we have near shore, maybe some shales or siltstones, and then some clay here. Walter would state that this same sequence would repeat itself, not just vertically, but also if you went laterally. Like this case, if we saw this in a canyon wall, and if we walked toward the east in this case, at some point we would encounter this near shore siltstone and eventually that sandstone at some distance. So that's that lateral distribution. So the concept that the vertical succession of facies reflects lateral changes in the environment. So remember, this word facies describes minerals, or in this case it's going to be a group of rocks that define a specific environment. In this case, for the sand to silt to clay, we're looking at a marine environment, especially when we look over here for this column here, column B, sand, silt, clay, limestone, right? So that's showing us that we call this a sandstone shale. Usually we call these shale, limestone facies. So sandstone, shale, limestone facies. That means it's a marine environment. And Walther also explained this idea of transgressions and regressions. So when the geologist sees this sequence from sands on the bottom to marine rock at the top, that means that sea level has changed. It's gotten deeper because these limestones form in deep water. Beach sand is on the shore. So here in this one position, sea level increased, and we call that a transgression. So when sea level rises or the land subsides, we call that a transgression. On the other hand, if we had sandstone over shale over limestone, that would mean that sea level dropped, and that would be a regression. We'll say more about that in a moment here. Now, again, for these vertical successions, we have these bedding planes, and bedding planes really separate individual strata from one another. And the key thing about a bedding plane that separates two individual beds is that bedding plane represents a change in the environment. Either you went from shallower water to deeper water in the case of sand, beach sand, to shale. So obviously there's a change from being on the shoreline to suddenly being underwater, or to limestone where you go into deeper water. So strata can vertically grade from one rock to another. Rocks above and below the bedding planes vary in composition, texture, and color. And that's just because of the change in the environment. So results from rapid change in sedimentation or periods of non-position erosion followed by deposition. So there's a change in the environment of deposition. So this outcropping here, this cliff, we see the bedding planes, right? And so each one of these represents some change. In this case, we mostly have sandstones and thinly bedded shale. So in this case, sea level is relatively shallow, or beaches here for the sand, and then we get a little bit deeper to get the deeper water shales, then it gets back to shallow. So there's some fluctuation going on here as well. In this chapter, we also talk about the principle of inclusions. So remember, for the relative dating principles, we look at superposition, lateral continuity, original horizontality, and then the other ones we look at are the principle of cross-cutting relations, and the principle of inclusions. And this principle of inclusions basically states that an inclusion of an older rock will be embedded in a younger rock. In this case, we have older fragments of granite embedded in a sandstone. So we know the sandstone's younger than those granitic clasts. And remember, the word clast means broken. It's a Greek word which means broken. So these are broken granite clasts or granite clasts. In this case, in the Sierra Grande here, we have some broken mafic rock. It's this darker mafic rock that's broken up. These are inclusions in a lighter colored granite. So these would be the mafic inclusions that are older than the granite itself. And another thing we look at are, especially when we try to get ages for sedimentary rocks, because it's really hard to date sedimentary rocks because they don't have minerals that crystallized during the formation of the rock. There is glauconite, but glauconite is a mineral that loses argon, so it's really not useful. It gives you a minimum age. But lava flows and volcanic ash, they're an event that can be dated with geochronology, and they can give us constraints onto the age of the sedimentary rock above and below it. But there's a couple of different things going on here. There's a lava flow, which is a surface feature. And so for the lava flow, you would see a big zone only on the bottom of the flow, right? Because remember, it was hot and it burned the adjacent, or in this case, subjacent rock. And then over time, there's erosion and weathering. If more sediment is deposited on top, you may see fragments or inclusions of the older lava in the younger sediments above, right? So clasts may be present in overlying younger rock. Again, lava flows only have a burn zone or bake zone on the bottom. Another type of igneous rock is a shallow intrusion called a sill. And remember, sill is conformable. It goes between weak zones of pre-existing layered rock. In this case, the sill has penetrated between two stratified units here. And note that there's bake zones on both sides, the top and the bottom. And then we're maybe seeing some inclusions of either number 4 or number 2 inside of number 3 here. So the sill would be younger than these stratified units because they came in later on. So that's one thing to keep track of, is using this bake zone to try to figure out whether it's a sill or a lava flow. Sill is going to be younger, probably younger than even number 7. It came in later on. But for the lava flow, it would be, the lava flow in this case is going to be older than number 4, which is obviously older than number 5 and 6 based on superposition. And in my previous lecture, I talked about unconformities, and I just want to mention here that your book calls these hiatus, so you can kind of refer back to that video. So I talked a little bit about facies. Remember, the key thing about facies is it's a group of rocks that define an environment. So when I see this, usually this symbol means it's a shale. So this symbol of little dashed lines means it's shale. So that would be a facies that's a shallow water marine. It's underwater, usually in the marine environment. And then when I see this stipple pattern, that's usually a sandstone. And so that's near shore. That's going to be right on the beach, usually near really shallow waters near the coast or on the beach itself. And then in this case, we're seeing some intertonguing, right? So, and some units can pinch out, but here's some lateral gradations. So this is a good example of Walter's law, how things can change laterally. And then we talked about marine transgressions and regressions a little bit. So the Grand Canyon, this Tonto group, which are the first 3 formations, Phanerozoic formations in the Grand Canyon, document one of these marine transgressions. So remember, below this Topete sandstone, this is a great non-conformity. Below here we have the Vishnu schist and the Zoroaster granite. These are Precambrian. And then we have the Cambrian sandstone, which is the Topetes here, and then the Bright Angel shale and Mauve. So again, thinking about the facies. So sandstone, that's going to be near shore, a beach environment, so near the land. But then shale, well, here the facies for this one tells us that it's underwater, a little bit deeper water, farther from shoreline. And then limestones form in even deeper water. So here we're seeing a progression from shallow water to deep water. So in this one location, sea level increased. And when sea level rises like this, we start seeing different depositional environments, different facies. Remember, each of the bedding planes represents a change in the environment. In this case, we went from shallow marine to deep marine in this case. So that would be marine transgression. So here's another view of that. So at time 1, we see the deeper water limestones, the intermediate water shale facies, and then the sandstone facies would be up near the shore and the beach. And then as sea level rises, you see that we start seeing the deeper water facies moving closer toward the land, right? And then if we look through a cross section here, we'll see that we have the basement rock, then we have sandstone, shale facies. That whenever you see that sequence, we're seeing a marine transgression. Whenever limestone's at the top, marine transgression. Let's look at one where we're seeing a marine regression. So in this case, we have higher water stands here, limestones forming deeper water, shale facies in the middle here, and then sandstone near the shore. But as sea level drops, you'll start seeing that we start depositing sand on top of shale and shale on top of limestone. So in this case, limestone on the bottom, shale facies in the middle, and then sandstone facies at the top, which is telling us that we have a marine regression. So just to review the transgressions and regressions, so we're seeing for transgressions, either the land is subsiding, some tectonics causes land to subside. We see glaciers melting, retreating. So when glaciers melt, all that water goes back to the ocean, sea level rises. Or maybe the sea level, or maybe seafloor spreading increases, which means there's a greater thermal buoyancy causing the mid-oceanic ridges to get taller, which is going to displace water onto continents. For regressions, maybe there's the continental drift has moved a continent over a warm spot in the mantle, which causes the land to be elevated. Maybe glaciers expand. There's an ice age, right? So that can drop sea level. And then maybe the rate of seafloor spreading decreases, which means that the mid-oceanic ridges will kind of subside, and which means the ocean basin volume will increase, sea levels will drop. So what can be some of the causes of these transgressions and regressions? So how extent they are, the rates of these marine. So since this Neoproterozoic time, which is going back to maybe about 700 million years ago, we have seen 6 major transgressions, regressions in North America. In fact, this course, as we go on into talking about the geology of North America, we really kind of look at it in these sequences. And the first one we talk about is called the Sauk sequence. And the Sauk sequence is a transgression which deposited that top-eat sandstone, the Bright Angel shale, and then the mauve limestone.